Okay, so for today's demo, end of sprint demo, I'm going to talk about uh, the extended Berkeley packet filter. This is also called ebpf. So what is ebpf? Maybe because this is an abstract concept, but hopefully by the end of this presentation you can understand a little bit about what it is and what it's used for. But ebpf is a flexible and efficient virtual machine-like construct in the Linux kernel that allows you to execute bytecode at various hook points in a safe manner and access a subset of kernel functions and memory. It's enabled by default in most Linux distributions. It's used to extend the capabilities of the kernel without requiring a change to the kernel source code or to load kernel modules. So this means usually whenever you need to use some a Linux kernel module, the idea of ebpf is to bypass that, and so it doesn't use a kernel module, and the operating system guarantees safety and execution efficiency as if it were natively compiled with the aid of a these programs are natively compiled by a just-in-time compiler and verification engine. So again, what is ebpf? So here we have a comparison of what a Linux program or module is and compared with ebpf. So on the Linux side, usually we have the main purpose of the Linux kernel is to abstract the hardware or virtual hardware and provide a consistent API to allow the applications to interact with the resources. Whereas here in ebpf, this allows for reprogramming the behavior of the Linux kernel without requiring changes to the kernel source code or loading a kernel module. So yeah, I guess the idea of ebpf programs is to interact with the hardware as well, but without using necessarily the kernel modules, which are sort of part of the Linux of the Linux kernel. So here we'll explain a little bit of how it works, but usually you'll have a program. Sometimes these programs need to do a system call or a elevated privilege, let's say execute a system call with elevated privileges. And in Linux here, for example, with a system call, you could interact with the different hardware that you have, but in this case you can bypass the Linux modules by using ebpf programs. So, but this is a complex subject, but let's just continue. So, ebpf programs are run by the kernel when events occur, so they can be viewed as a form of function hooking. Events can be generated from kprobes or user probes, as we'll see later on in the demo, trace points, dtrace probes, sockets, and more. This allows to hook and inspect memory in any function at any instruction in both the kernel and user processes, to intercept file operations, inspect specific networks, network packets, etc. An event triggers the execution of an attached ebpf program, which then can store information in maps, print to ring buffers, or call subset of kernel functions defined by the API. An ebpf program can be attached to multiple events, and different ebpf programs can also access the same map to shared data. So here, for example, let's say that you're interacting with the network layer. You can set up a program that whenever, let's say that Linux receives a syscall, send or receive message, which is the networking sort of low-level, let's say, function calls. You could have a program that acts according to one of these functions, as mentioned here, like a function, and you can hook this function to different parts of the kernel. So you can hook it here, for example, at the at the syscall level or at the TCP/IP level. Maybe you can set up a probe further down in the network stack or anywhere where you like when opening a file, and these types of things, as mentioned sort of here. Yeah, you can trigger an event that's attached to a BPF program anywhere in the stack, and yeah, okay. So maybe hopefully we'll look at a demo, because this is a so how does a ebpf program work? ebpf programs are run by the kernel when events occur, so they can be viewed as a form of function hooking or event-driven programming. Notice here that you're sending these are events, send receive messages, and you can have a program that's performing something when these events are occurring. So events can be generated from K probes, U probes, trace points, dtrace probes, sockets, and more, as we talked about earlier. This allows to hook and inspect memory in any function that at any instruction in both the kernel and user processes. So either here or up here at the user level. To intercept file operations, inspect specific network packets, etc. An event triggers the execution of an attached ebpf program, which then can store information in maps. So this is like a data store, so to speak, similar to what you can think of like a Redis or some of these. It's just a map that stores information for that later, I guess, another program can access this data. So it stores information in maps. It can also print to ring buffers or call a subset of kernel functions defined by a special API. And an ebpf program can be attached to multiple events, so different types of events. There can be some other types of events here, like in the file operations. And you can also access the same map to share data, as we mentioned earlier. So maybe an example would be, let's say that we have a packet filter here, and our packet filter intercepts a filter that we do not want to pass to one of our programs. So we could intercept that here, and maybe handle it with some other program, or I don't know. This is just a shared storage, so to speak, between programs that we can use between ebpf programs. So what are the main components of ebpf? What are the main ebpf components? So these are all pretty much the components. Notice that we have a just-in-time compiler, a verifier. We have a program that needs to execute root access, or another program that needs to have root access to the network layer. So there are different components, and I'll talk about all of these right now. But in essence, the first thing we have is hooks. So ebpf programs are event-driven and run when the kernel or an application passes a certain hook point. Predefined hooks include system calls, function entry/exit points, kernel trace points, network events, and several others. And actually, I'll try to do this. So here you can set up the hook point to be at any part of the stack. So you can have it here, maybe. There's another image. I don't think like. You can have it here between the system call and the Linux. After the system call. So there are different pieces, hook points where you can attach your program. Next we have a just-in-time compilation instruction set, which is right here. So what does this do? So whenever the desired hook has been identified, the ebpf program can be loaded into the Linux kernel using a bpf system call. This is typically done using one of the available ebpf libraries that we'll try to demo also. Um, and as a program is loaded into a Linux kernel, it passes through two steps before being attached to the requested hook. First, there's a verification step, um, and the verification step ensures that the ebpf program is safe to run. It validates that the program meets several conditions, such as that it doesn't run into like endless loops, or the program is um, the program is a closed system, so to speak. And then it has a just-in-time compiler, which translates generic bytecode of the program into the machine-specific instruction set to optimize execution speed of the program. So it compiles it down to the CPU, so to speak. Next, we have helper functions, tail calls, safety features, pseudo file system, and infrastructure for allowing ebpf to. Oh, okay, so this is optional, where you can have like infrastructure to allow BPF programs. If it's very compute-intensive workloads, you can offload it, for example, to a network card. But let's talk about tail calls, safety, and pseudo file system. And maps, actually. Let's also talk about maps. So the maps is a vital aspect of ebpf program, and it's the ability. It's a sort of data store that provides the ability to share collected information and store state. So here, I guess the idea is to act as a data store where you can share information between different processes. So ebpf programs can leverage the concept of maps to store and retrieve data in a wide set of data structures. And so some of the data structures that you can store in this map are hash tables, LRUs, least recent used, ring buffers, stack traces, LPMs, which stands for longest prefix match, and many others. But just to shorten the description, it's just a data store. Now, helper, tail, and function calls. So these tail calls are used for calling into other ebpf programs. Some safety features that this ebpf programs have are security hardening primitives. So for example, there are several layers before executing one of these programs that the program will go through. So the first one is that you need the required privileges to execute one of these programs. There's a verifier process that where programs are validated to ensure that they always run to completion. That's what I was talking about a little while ago, that they don't just kind of loop infinitely. Programs may not use any uninitialized variables or access memory out of bounds. Programs must fit within the size requirements of the system, and programs must have a finite complexity, where the verifier will evaluate all possible execution paths and must be capable of completing the analysis within the limits of the configured upper complexity limit. That just means, yeah, like not having loop and endless loops, so to speak. Then, upon successful verification, there's a hardening step here after the verifier, where the program will just try to protect it against different known vulnerabilities, such as the Spectre vulnerability, which is a CPU a CPU exploit that I guess just exploits the fact that modern CPUs try to perform branch prediction, but that's way too detailed. Anyhow, so these are the components of ebpf, and sorry for getting too low into the weeds, to the details. Maybe okay. So what are some common use cases of ebpf? So as we'll show later on in the demo, there's a lot of development around these types of programs, mainly used for security, tracing and profiling, networking, and observability and monitoring. So a lot has to do with like the network stack and also security layer. And I guess there's a lot of modern applications or that are currently being developed that leverage this ebpf programs. So I guess as a common example, Cilium. Cilium. Usually, whenever we deploy a Kubernetes cluster, we will need to have a CNI, a container network interface, that allows for pods to communicate between different nodes and all of this. And Cilium is an example. Also, Calico, which are Calico is the most used network CNI right now, and they're currently extending sort of their network programs to use ebpf. And also Cilium is another CNI that's currently developed by, actually I'm not sure who develops Cilium, but they also use ebpf, as well as many other sort of security and observability components. Okay, so let's see. Let's go back to slideshow. So how can we write an ebpf program? The main idea would be that you have I guess an SDK, software development kit, written in Rust, Go, C or C++. I think those are the only ones supported right now. And these SDKs are just a wrapper to actual ebpf programs. So an ebpf program could be thought of as similar to an IP tables program. So instead of having to deal with all that complexity of filtering, you can leverage one of these wrappers. So in our demo, we're going to use the Go library. So after you write the code in whatever language you prefer, with SDK, you can compile the program to bytecode, or actually the SDK will help you do this. So why to bytecode, you may ask, and the reason is that the Linux kernel expects programs to be loaded from in the form of bytecode. So after, I guess this is the only thing we need to worry about as developers. The library will so user space sends bytecode to the kernel together with a program type, which determines what kernel areas can be accessed. And this is already part of sort of the BPF portion. Then the kernel runs a verifier, as we just talked about, on the bytecode to make sure that the program is safe to run. The kernel just in time compiles the bytecode to native code and inserts it to a specific code location. Then the inserted code writes data to ring buffers or a map, as we talked about, depending on whatever logic we coded. Maybe there's an event that we want to observe and write to the map every time something happens. And then the user space reads the result values from the shared maps or ring buffers. That's I guess how you would write a program. So right here, ideally here we have our Go library, and yeah, which is a wrapper to the Go program, and we can access maps and observe system calls and whatnot. So yeah, that's pretty much the theoretical piece of it. Now let's go ahead and look at a demo. For the demo portion, so here we have, for example, we have an different ebpf programs, which I'll show right now. As an example, here we have like 12 different use cases. So these are our examples, and these examples are actually taken from Cilium eBPF. So their documentation has all of these examples, and these are just sort of explaining how they run it. And they use, I think Cilium are the guys that developed the Go wrapper to eBPF programs. And since we're gonna execute this in Go language, so that's why we're using this wrapper right here. Specifically, we'll be executing these examples and talking a little bit about what each of them does. So yeah, this is Cilium. They, as we mentioned, they developed the Golang package. So okay, just to not take too much additional time. So let's go ahead and try, for example, one execution run. Okay. So as we mentioned, these are heavily used, or this eBPF programs are heavily used, like in security, sort of related. Let's make this a little larger. Okay. So let's go ahead and execute the first one. So for the first example, we'll just execute 3 to not take too much time, but just to get a sense of it. So for the first example, we're going to execute an XDP, which is a network packet filter that runs in the receive path of a device driver. So here, for example, I have a network device. The network device that's on this laptop is this one, the ENS2, the physical device, EN2P0. So here we're gonna execute a program that's gonna attach itself to the network device. So something like what we showed in the slides. So I think okay, I think I closed it, but this specific program is it's gonna attach itself to this device, and it's gonna parse IPv4 sources addresses for the packets, and it's just gonna write how many packets we're receiving from each source. So let's go ahead and execute. Okay, so here we're listening on events that come through this network card, which is the only card I have here right now. So notice here that we're receiving, these are packets that we're receiving from different sources. So as an example here, let's go ahead and, so we received like nine from this one, and we can go and check, okay, what is this source? And maybe it has to do with okay, so this is coming from Cloudflare data center. So I might be opening something, maybe a web page or something that comes from Cloudflare. So that's, I guess, the main idea of this, the first one here. And we're just performing. So for example, here we can analyze and say, okay, what's the highest network count right here that we're receiving? And so the highest network count is this guy right here. Let's go ahead and see, okay, what is this? Or even one of these. Is this the same one? Yeah, Cloudflare. Okay, let's try a different one. And this here, Discord. So since we have our Discord open, we can notice that, and we're transmitting and all of this. That's why we're getting the Discord server right here. So that's the first one, and you may now infer, okay, why these are heavily used in security sort of systems. Maybe one more example here. Let's see. So this one. So notice here that I'm executing as a user, as a common user, and without root access. So who am I? I'm just a regular user. But whenever we execute this, let's say that we want to analyze, okay, who is accessing the elevated sudo privileges. So for example here, I'm going to open a second terminal, and I'm going to write, I don't know, just any command like date. Okay, I think this is then intercepting any bash command, but let's date, I don't know, something else like touch abc.txt, and you can pretty much intercept any call to the bash to bash. So here, for example, okay, this is because this is a user space probe. So this is specific to user space. Now let me try and execute as a root. So su. Hold on. Okay, so I guess that this is running both of these, but it's intercepting the user, not necessarily I misspoke a little while ago. This is not system calls. This is more like user calls. But now let's see, maybe one, maybe just one more. Okay, so this one. So this is this program right here is going to be attached to the system call interface. Let's see. Let me see if I can. So just to give a sense of what's going on. So the first example we showed, it's a program that we're attaching here at the network layer. Then the next one we attached, I think, somewhere up here in user space. Now the next program that we're going to run is going to be attached here at the system call level to intercept any elevated privileges. Let's go ahead and close that. Maybe this is, hold on. So this one, this is the system call one. Okay, so the program is running and waiting for events. So here, for example, now if I do date, oh, it's still executing. So I have to explore this a little more, but let's say I want to sudo vsudo. This is this requires elevated permissions, but it's capturing all of this information. So I guess with that, maybe this is just to get a sense of what ebpf programs can do. There are many types of things, and I think that's all for the demo. Any questions?